Okay, so I'm gonna just do a regular slideshow today. I'll keep working on figuring out how I can share, do the live slides recording with everyone, which is quite unfortunate. Okay, so let me see if I do this now. Okay, so now I am gonna share my screen, position on screen left. Okay. Okay, now tell me that you can see my slides.
Yes, we can see it.
You can. Okay, excellent. Okay, everyone, welcome to another feature of numerical methods, and I'm gonna go to the correct slide this time. Last time we left off, we were talking about the number of iterations and detecting what some have called convergence. And if you remember what happened, we were solving this system of equations. It had three unknowns, so x1, x2, x3. So those would designate different quantities in real life. And for each one of those, what I'm showing here in this table is what we obtained in the Python notebook last time. And initially, you start with the initial guess, 1, 1, 1 in this case, and then you start improving that guess. And then after a certain number of iterations here in the first column, you reach a point where the solution is not really changing that much. So over here, for example, after 30 iterations, 35 iterations, the solution is not changing for all of those three numbers. Okay, all of those three solutions. And so we said it would be silly to say, run 100 iterations or 1,000 iterations and then just keep churning on numbers inefficiently, right? We need a mechanism to tell the iterative solver, stop right there. You're not doing any better with these numbers, so I would like you to stop. And we talked last time about calculating an error between the different iterates. Would someone remind us of that? So I know a couple who were involved with those definitions last time, but if you remember what we talked about, would you mind repeating that to us if you'd like? Let me see. Got many of you over here. Okay, so looks like I'm gonna get that wheel of randomness. Do I have any takers?
I can go ahead really quick.
Okay, Sammy.
I think last time we were talking about using the relative approximate error.
Yes, and yeah, so it's the difference between the current iteration value and the previous iteration value, correct? And divided by the current iteration value to give us a relative number. And then we say, but that is going to give us three errors, correct? In this case, it's going to give us one error for x1, one error for x2, one error for x3. Okay, so let me show you this. Just like Sammy said, if we look at the approximate relative error or relative approximate error between iterations, what do we get? This is specifically for this case. As you start reaching iteration, let's say 30 over here, your relative approximate error, 10 to the minus 7, 10 to the minus 9, and 10 to the minus 9. For each one of those solutions, you have a different error, correct? So then which one, that was the second question, which one should we choose to say stop? Take a minute to think about it. Abby, I saw you unmuted yourself. I'm not going to let you talk.
Yeah, it's because last time we talked about.
Yeah, yeah, I know you know the answer, so I want someone else to say it.
Okay, yeah, sure.
I was going to say, Abby said last time that it was the one with the largest error.
Okay, that's right. So Sarah and Abby, and what we talked about last time, they said, look, let's pick the worst one. Okay, the worst one, while the worst one is gonna produce the largest relative approximate error. That's gonna be the guy that is converging the slowest. Okay, that's gonna be the solution value, x whatever xi. So x1, x2, x3, whatever, one of those is going to be converging the slowest. In this case, x1 is converging the slowest because it has the largest error. It's 2 orders of magnitude larger than the other 2. So Abby and Sarah were suggesting, hey, just take the maximum of those 3 errors. Take the maximum of those 3 errors in magnitude. So take the absolute value, of course. So if you had calculated it with an absolute value, it would be positive anyway. Take the largest one and keep looking at the largest one. Every iteration, look at the largest error and then stop when the largest error is below a certain tolerance that you specify. So the same way that you can specify the number of iterations, you can also specify a tolerance. You can tell the solver, I want you to stop after a certain relative approximate error has been reached. Typically, 10 to the minus 10 maybe, or 10 to the minus 5, depending on what is important for your solution. If you're dealing with large temperatures, for example, where an error of 2 degrees is not going to be a big deal, then you can set your relative error to 1 or 10. Okay, but if you're talking about quantities on then that are of order 1, so 0.5 and 0.7 and 0.3, then an error of 10 to the minus 5 might be more appropriate. Okay, but that's up to you to choose. Okay, so now to formalize this definition, choosing the largest value, that's not the only measure. I think someone else mentioned last time also that we can take the magnitude of the errors. So we take E1 plus E2 plus E3, some magnitude. And so let's formalize that definition. Together, those 3 errors, or all the errors in the solution, if you had a system of equations with 1,000 unknowns, you would have 1,000 errors. Agreed? And those 1,000 errors together, you can either take the max, okay, or you can take a collective measure to take a magnitude of them. So to formalize this, we take all of those errors together and define a vector. Okay, just a vector, standard vector, E1, E2, E3, E4, E5, etc. Okay, and then we recall the norms, the vector norms. We say the vector of the errors, I can define a norm. And what is a norm? It's simply a measure that measures the size of the vector. The Euclidean norm with the Pythagorean norm, that's the standard definition of the vector magnitude, the length of the vector, which is the square root of a squared plus b squared. Do you remember that? The side of a right-handed triangle, for example, the size of the diagonal is square root of a squared plus b squared. That's because you can form 2 vectors, a vector a and b, and the magnitude of that vector is that length. Okay, you can do the same here. You can take the square root of E1 squared plus E2 squared plus E3 squared, and that's completely legitimate because that gives you a measure of the sense of the error. Okay, there are other norms to be defined. There's what we call the one norm, where you take just the summation of the quantities. So E1 plus E2 plus E3. Okay, you just take the sum of all of those 3. Okay, or an L2 norm, where you take the summation of each one of those square root of each one of those squared. Or you take the infinity norm, which is what Abby mentioned last time. The infinity norm is simply the maximum value of that vector. Okay, so they're right over here. And in Python, you can access the norm of a vector by calling numpy.linearalgebra.norm. Over here, A is the vector of the errors, or just a vector, that has just a one-dimensional array, essentially, or a one-dimensional list has, values in it. Okay, so you do the L1 norm, L2 norm, or infinity norm. Okay, and then we can simply compute the norm of the error at each iteration, and then stop when the norm is below a certain tolerance. So for example, for this problem that we were solving, E1, E2, E3, we had 3 values in the vector. You compute the L2 norm here in the column to the right, and that gives you a single value. That's what the norm does, right? It takes a vector of an indefinite number of entries in it and summarizes it into one value, and then you can check that value if it's below the tolerance or not. So in this case, I would keep checking the L2 norm at every iteration. And once I hit a tolerance, let's say my tolerance is 10 to the minus 8. So then I would stop, somewhere between iteration 30 and iteration 35, because that's where I hit the norm of 10 to the minus 2. Okay. Okay. So now which norm would you choose? It really doesn't matter, as long as you are clear about it. Because in practice, most of those, if you're solving the same problem, stopping at using different norms, they're going to differ by probably 1 iteration. That's not a big deal. Okay? It really doesn't matter. Okay? The max norm is like the hardest one. It's just makes sure that the worst converging quantity, we hold that accountable, right? Rather than a sense of average. Okay. Now, what we did here is we looked at the difference between iterates. Okay, saying, okay, this number is not changing much. I really, really like that definition, because that gives you a sense of, this algorithm on this computer using this this programming language, that's the best it can do. It cannot improve those numbers anymore. It's not improving those numbers. So you know what, that is, think of it as a device. Think of the Jacobi solver on that computer is just a device. The device cannot do any better measurement. So let's say you're taking the temperature, for example, at your house. If it's just going to give you one significant digit after the decimal point, that's the best it can do. If you want something better, you got to get a better device. Okay, so we're going to change solvers later. But there are other measures as well. Okay, there are other error measures, right? Rather than just looking at the approximate relative error, that's not the only one. There are other error measures that we can define and hold the solver accountable to. Now, if you think about this, we are solving a system of equations, AX equal B, correct? We are looking for X. When we find if we find the exact solution, then AX is going to be equal to B exactly, correct? So we kind of know what the answer should vary. So we don't know the answer X, but we know if the answer is found, then if we plug it back into the governing equation, AX is going to be equal to B. So can someone now suggest to me another error measurement? Not the norm, just a different error measurement. Right now, we measured the error between iterates, iteration K and K plus 1. What is another error that we can define?
Could you like,
yes, so can you, who's speaking?
Oh, sorry, this is Porter.
Porter, okay.
Yep.
Go
so
ahead.
Could you just like plug it, like basically just plug in your solution measure that you found into the matrix and then compare how close your answers are to what the right-hand side vector should be?
You got it. You got it. So Porter is saying, look, we have the governing equations for this system. Okay, why not take every iteration that we hit, every iteration that we do, and plug it back into the original system? So in other words, take the iteration K, all the values, the iteration K, multiply them by the A matrix, okay, and see how far they are from B. Because we know that AX needs to be equal to B. But we don't know the exact X. We are close to X, to the exact X. So then if we plug the approximate X in this system, then we can measure how far away we are from B. And we define this as it's a sense of a true error. Somewhat, look, it feels like it's a true error. I'm gonna call this an absolute error measure. Don't confuse that with the absolute value, okay? In the linear iterative solver community, they call this an absolute error. So in other words, I'm taking x, now this is not to the power k, that's iteration k. So I'm taking the x vector that contains x1k, x2k, x3k, the kth iterate of all the entries in my solution vector. And then I'm taking the difference with the right-hand side vector b, okay, ax k minus b. And I define, but that is going to be a vector, correct? That result is a vector. And then I take the norm of that to give me one number. I need one number, one value. And then I check that against the tolerance, okay? So Porter, let me ask you this. What would you then say you want a typical tolerance to be in this case?
So within, I would say like within a certain percentage of what B should be, like what your.
So now
right
you're
hand
thinking relative error. You're thinking relative error, but yeah. So but in absolute, we really don't know. Ideally, this should be 0, correct?
Oh, right.
But because that's the true system, but we don't know because we don't know the scale of the system. It's going to depend. Again, are you dealing with temperatures on the order? Are you solving for the temperature in radiative environment in outer space where temperatures can be 5,000-6,000 degrees, where an error of 10 degrees is not going to be a big deal? Or are you dealing with things on the nanometer scale where, you know, if you mess up a 1 nanometer, you're going to blow the entire system, right? So it's still hard to tell. But you know, the error measure in this case is going to depend on the scale of your system. So take that into consideration. You'll see in homework 4, which is due today, the homework 4 due next week, I'm going to choose a tolerance based on the absolute error of 0.5. Because I know the system that I'm dealing with has temperatures on the order of 100. Okay, so 0.5 is a pretty darn low error in that case. Another definition of the error is if you know the exact solution, then you take the difference between your iteration and the exact solution. Now, this is useful for verification purposes, as we do in numerical methods, okay? And another absolute error definition is the difference between iterations, but without scaling that difference, okay? So just xk minus xk minus 1. Now notice all of those quantities are vectors. That's why I have the norm symbol. Those are the 2 vertical bars around the vector. I hope you've seen this before, okay? Because you need to condense this into a single value so that you can compare to a tolerance, okay? Now on the other end, we can take those definitions and do a relative error. We already did the relative error for the difference between iterations, okay? Excuse me, but then we can do a relative error just like what Porter suggested, a percentage of B, somehow a percentage of B. So you can take that true definition of, you know, the linear system itself and scale it by B, okay? So then that makes it just relative to the system. And now in this case, you can start thinking of errors in the order of 10 to the minus 5, 10 to the minus 10. Okay, because when you scale it, then everything is with respect to 1, in other words, you know, if you want to use the lingo used in the community. Or the error that we just were talking about. We take the relative approximate error, okay? Okay. Now we define now that we know what the error, how we define an error, you can choose whichever one you want. In the homework problems, in homework 4, I'm going to ask you which error to choose, okay? But in real life, choose whichever one you want. Hint, I really like the last one. I really like that last one, okay? But you can choose whichever one you like. And, you know, as you mature in your engineering knowledge, you will know which one to choose. It's like, I don't know, that the matrix or something is like, yeah, you will know, you know, so you will know. Now for convergence, we kind of already defined that. Now you take that error and say, once that error is less than a tolerance that I chose, then stop. Okay, then just stop. So now we have two control knobs on our iterative solver, the max, a number of iterations, and a tolerance. Okay, typically we always check the tolerance first, but we also want to make sure we don't overdo the iterations. What if you made a bug in your code? What if the system is unsolvable? Okay, you might take hundreds of thousands of iterations and not converge to a tolerance at all. So what you want to do in that case is put a maximum number of iterations. And that could be an option that you will also pass to your iterative solver and say, okay, I'm going to solve A, X equal B. This is A, this is the right-hand side. This is my guess. I want you to stop after a tolerance of 10 to the minus 5, but also don't do any more than 100 iterations. I see this in my research all the time. Sometimes I have what we call ill-conditioned systems of equations that I'm solving for the pressure, and I end up taking more than 1,000 iterations, and that's very expensive. So I just tell it, do no more than 100. And I know if my system is not converging within 20 iterations to the desired tolerance, I have an issue with my system. So then I go and change my boundary, I change things in the system, okay? Okay, so we already talked about the these iterative solvers, and I'm showing you here the code for the Jacobi algorithm, and you already have a copy of that. And I'm going to give you for homework 4, I'm going to give you both the algorithm for Jacobi that takes in a tolerance and a maximum number of iterations and an option for which norm you want to choose. Do you want the L2 norm, the L infinity norm, etc. Okay, so you will be free to use those in your homework. Okay. This is the other version of the Jacobi. I do not advise using this version because we cannot change it to do the Gauss-Seidel solve. Okay. Everyone on board with me? See, in the classroom, I would be reading your body language. I know most of the time, and I'm pretty darn good at that. I know who's like, huh? What is he talking about? But I can't hear. It's hard for me. Even, with your camera, I can tell a little bit. But most of you have your cameras turned off. So I'm gonna rely on you, please, to tell me if you disagree with something or you have a thought. Okay?
I have a quick question.
Go ahead.
So just a thought, I don't know that it's fully formed yet, but like one of the reasons we were using these like a tolerance level and calculating the error is to help us not do too many iterations, because that would be like wasted power or just trying to do something that's pointless. Mm-hmm. Is it sometimes more expensive to use an error and calculate that as opposed to just doing a certain number of iterations?
No, you always want to stop at the error, because that's ultimately what defines if your system has converged. Because then you can say, oh, I have converged to a tolerance of 10 to the minus 5 based on this error. But you can't say, oh, I ran the system for 100 iterations. Like, what does that mean? It's not quantifiable, okay? So we always hold the tolerance, the error, accountable. But we got to make sure that we also don't overdo the iterations, because if you're not reaching that tolerance at all, then you would be spending thousands of iterations. That's not useful. Okay, don't do that. So that's why we put in maximum iterations as well. Okay. All right. Now we're going to talk about our next solver, which is the Gauss-Seidel iterative solver. Okay, so now since we are in the world of iteration, last time someone said, okay, we are someone said this iterative solver reminded them of a PID controller. Are you with us today? And they said that, you know, there's a factor, there's a coefficient that you can change to get closer to the solution. Okay, so this is our first step now in taking the Jacobi algorithm and making it better, making it slightly better. Okay, now here's the observation. If you look at the Jacobi formula, actually, let me go back to the Jacobi formula. Where's the Jacobi formula? Jacobi formula is over here. Okay, here's the Jacobi formula. Notice what the Jacobi formula says. It says the new value is equal to the old value plus some correction. Now think about this. You've gone over, I tells you which solution entry you're in. You know, that's the point on the heat transfer rod. Or this could be, you know, your salary or whatever unknown you're solving for, okay? So you start with X0 or T0. You update that using the old value of T0, okay? And then you go to T1, okay? And then you use the old value of T1 and then move on. Agreed? Now, on the right-hand side over here, so this is still saying new value of Xi is old value of Xi plus something. Now notice this correction term. This correction term only depends on the old values. So again, for X0, you're taking new X0 is old X0 plus everything on X0, X1, X2, X3, old. You update X0, now you go to X1. And then you say new X1 is equal to old X1 plus sum with everything X0, X1, X2, X3, old. But we just calculated a new X0, correct? In the first step, we calculated a new X0, then we went to X1, but in this summation term over here, we're still using the old X0. So make me a suggestion now. What if we use the most recent X0? And in X2, it's going to depend on X1. In this Jacobi, it will depend on X1 old and X0 old. But we already computed new values for X0 and X1. So why not use those? Why not use the most recent information that we computed? Do you see how this is happening? So first you solve for X0, and then go on X, you update X0, and then you update X1, you update X2, you update X3. In Jacobi, so this formula tells you that all of them, they depend on all of each other. So X1 depends on X0, and X2 depends on X1 and X0, and X1 as well, right? And X2 depends on X2 and X1 and X0. So why are we using the old stuff? Why don't we use the most recent values? Turns out that when you do this, you can generally cut your number of iterations by half. So instead of doing 40 iterations to converge to a tolerance, you can do it in 20 iterations. And that's called the Gauss-Seidel iterative solver. So, like I described, the X0 is updated first, and then X1 is going to use X0. Let's use the most recent values. So always use the most recent information. So we're going to take the Jacobi formula, Xik plus 1 equal Xk and Xk. Notice the explicit dependence on K, which is previous. And we're going to knock out those Ks. And what we're going to say here is we're going to use the most recent information. Just use whatever is available in your array. So as you are updating your array, just reuse it. Keep reusing it. And you'll see this in the code. It's actually simpler because you don't need to store an old copy and a new copy. You only store one solution vector and you keep reusing it. Turns out by doing this thing, you can improve your convergence rate. You can double your convergence rate. Okay. So the Gauss-Seidel algorithm, and I'll give you the code. is similar to the Jacobi, except we use the most recent information. That's an exam question. What is the difference between the Jacobi and the Gauss-Seidel? But I want you to understand it. Do it by hand, okay? We're gonna do this example by hand. Do it at home by hand. So I'm gonna give you this example, okay? So that's the same example we worked on before. We know the exact solution over here, and we start with an initial guess 1, 1, 1, and we're going to use this update formula for Gauss-Seidel. Xi new is equal Xi most recent, not old, just most recent, the most recent values that we got, whatever you have available. For the first iteration, X1, we are forced to use the old values with X1 because that's the first entry in the solution, okay? So it's X1 plus 1 over 5, that summation, 5X1 minus 1X2 minus 1X3. And over here, X1, X2, X3, we're going to use 1, 1, 1, okay? That's the initial guess. And that gives you 8 over 5. Now, when you go to X2, pay attention here. I'm going to try to be very advanced by using annotations. Okay, where's the annotation? Okay, I can draw. All right, clear. Okay, so notice over here, X1, X2, and X3, they're all using this guess. Okay, over there. Okay, now we go to X2. We say X2 old, that's gonna be this guy over here. All right, plus 1 over 3, 11, minus 2X1. Which X1 do we use? Do we use the one in over here or this one? Well, Gauss-Seidel says use this one. That's the most recent value that we got. In Jacobi, for this iteration, you would have used the one from the initial guess. Okay? And finally, X2, we only have an old X2, so we're going to go there. Get these tentacles. So speaking of,
Professor,
yes.
Braden speaking. Why does X2 not depend on X3 in this case? Oh, is it? Never mind. I see why. Because in our equation,
there's a 0. Yeah, there's a 0 coefficient. Thanks, Braden. Yeah. So I gotta erase these tentacles. Now, speaking of tentacles, my son is watching Finding Nemo. Was watching Finding Nemo the other day. Finding Dory, where she meets that octopus, and he tells her he has lost one arm. So she tells him, "You're a septopus." And my son asked me, "What's a septopus, Papi?" That's like, it's an octopus with 7 arms. Anyway, turns out there's a difference between tentacles and arms, and we can talk about that later. Anyway, okay. So now for X3, okay, we use the old value of X3 that's coming from here, okay, over here, and then X1. Which one do we use? 8 over 5, and X2 is 0. We don't have a X2 coefficient here, and X3 we gotta use this one. Okay, so you see how this works now. Okay. Now for this example, the Gauss-Seidel converges in about half the number of iterations. Converges to the same tolerance in about half the number of iterations, which is great. Okay, I'll give you the code for Gauss-Seidel, so you don't have to worry about that. Actually, we can just do an example right now. So I'm gonna stop. I'm actually gonna keep the share. Okay, go ahead and open up. Yes, Sarah.
Why do we bother with the Jacobi method then?
Because it's a great teaching, first for historical reasons, and it's also a great way to teach iterative methods, right? So remember where we were. Before you came to class, you had no idea what an iterative method was, I suppose. And then we looked at the Jacobi and we said, okay, we solve one equation, we say x equal b over a. Two equations, we solve equation 1 for x1, equation 2 for x2, right? So see the progression in linear thinking, right? And then now we improve that. And we're going to improve the Gauss-Seidel even more now, okay? So, so there are reasons to learn this, not that you're going to use them in life, but guess what? They are great teaching examples. They are a great way to start from scratch, okay? In practice, we hardly use the Jacobi, okay? There's no reason to use it. You're right, absolutely right. But this is, I'm teaching you a concept here, the concept of thinking iteratively, right? So imagine I had started with Gauss-Seidel. You'd be like, you know, forget it. I'm not gonna, I don't want to learn this, right? Okay, so let me start. Always good questions, Sarah, thank you. Let me start my Jupyter notebook. Go ahead and start your Jupyter Hub notebooks. And we're gonna do coding activity 5, LinSolve coding activity 5. Okay, so now we're gonna do the Gauss-Seidel. In your homework 5, you are gonna you're gonna be comparing Gauss-Seidel and Jacobi for the heat transfer problem. Okay, not this silly toy problem. You're gonna do it for the real system of equations with temperature. Okay, and you're gonna see with your own eyes that, boy, this thing is much cheaper, much faster than Jacobi. Okay. All right. So here's the notebook, coding activity 5. Go ahead and start executing the cells. I press Shift Enter. And again, we're going to solve this system of equations that we've been doing in class. It's just a canonical system. There's no physical meaning for it. And this is the Jacobi algorithm that we discussed last time. And we defined our coefficient matrix. So I got all of that in for you over here. A is, you know, this coefficient matrix. B and max, we define maximum number of iterations just to iterate for 10 iterations. Now we want to modify the Jacobi iterative solver to use the most recent data. I said that's the Gauss-Seidel method. So although I'm going to give this to you in your homework assignment, I want you to give this a shot on your own, okay? So the Gauss-Seidel method is the same as the Jacobi method, except we're going to use the most recent information. Now, to do this, I'm going to give you a few minutes. To do this, look at the Jacobi. In Jacobi, we create an X old, okay, which was equal to X gas therapy. Okay, and then we also created a new solution vector called X, if you want to call it solution, right? So we would update this new solution, but on the right-hand side, we were using X old. Notice Xi, then iteration for iteration K plus 1. Xi is equal to X old I plus all of this. For Gauss-Seidel, it's actually easier because you don't need an X old. So what I want you to try is just try to fill in these two blanks over here to see if we can use the most recent information. Okay, I'm gonna try to form you into groups. Before I give up on these breakout rooms. Okay, looks like some of you are individually in your own rooms. So I'm gonna try to move you to, hold on, because not everyone is attending class. Some of you might end up in your individual rooms. So think by yourselves, okay? I'm gonna form you into groups. Now, when you get into groups, start talking to each other, okay? Introduce yourselves to each other and start thinking, what would you do here? Start typing together, share your screens, whatnot, okay? So I guess I still, so for those of you who are still here with me, did you log in with the way I described in the announcement? And were you able to verify? Yes, Sarah.
Oh, I thought I did. I always clicked the link and I just double checked that I was using my UID and going through that. So I'm not sure who I'm logged in as, if I'm on my personal or on my thing. I'll double check that.
Yeah, because I still can see that you are not assigned to rooms. I'm sorry. But you gotta follow try to follow those instructions. So log in with lms-utah and then you can double check on your zoom.us. Okay, please try to do that so that we have everyone assigned to an appropriate room. Whether you do it now or later, that's okay. But for next time, what about the other? So Porter, for example, did you follow the instructions?
But,
pardon me?
So I didn't do it specifically today, but I logged in and have been working like consecutively. But I think I got into a Zoom room yesterday and that messed it up.
Okay.
I'm sorry. I always forget to log in that way too. I did it now, but I'm not sure if it'll do the room.
Yeah, it has not assigned you yet, but that's okay. Some of you don't have to do it now. Don't worry about it. But for next time, so that I can, you can work in groups. I just want you to try to solve this problem now. Do a couple minutes. All right, time. Okay, let's wait for some of the others to come back. Okay. Most of you are starting to come back. A lot of messages, chat. I see everyone panicking on the chat that homework 4 is due today. Well, you can blame that on the Mac operating system. Sometimes when I'm clicking a date, the cursor is finicky. It doesn't click the date I want, and it defaults to some other to date. So it's definitely not due today. All right, everyone, do we have any takers? Let's see. Classroom activity number. Let me see. Let me pick one. Hold on. Breakout rooms. Let me see. Group activity 9. So Jennifer and Quaid and Sovit. You guys have an answer for me?
We think it's going to be a 0, but np.0, but we're not so sure.
Okay, so here you want to say np.zeros of size n. Okay.
Yeah.
And then what about the other one?
We're still trying to figure that out.
Okay. So who agrees and who disagrees with group activity 9? Okay, let's see. Group 13, Harris, Megan, and Parker.
We did the same thing, the NP0.
Okay. Okay. All right. Let's see. Group 12. Do you agree? Disagree? So Adriana and Yongshu and Sean.
I agree with the NP0s thing that they did.
So let's assume for a moment that yes, MP.0s. Do you have then an answer for the second line, for the second question marks?
What would you do here? Well, we were thinking that instead of using like X old, we would use like the same X value that you defined the variable to be, so like XI instead.
Okay.
But
and then
we haven't completely formulated that yet, though.
Okay, so it's gonna look like, so you are correct. Yes, they're XI. Okay, this is XI, absolutely. And what about here?
Yeah, that's what I was looking at, because you didn't have like an array defined as that. I had it as X, but it gave me an error, so I was still trying to figure that part out.
It gave you an error when you put X over here?
Yeah, it told me it wasn't defined.
Okay, well, yeah, it should have been defined over here. Okay, so you are correct, Adriana. This is the formula for Gauss-Seidel. You're simply reusing the values in the solution vector. As you update it, remember this X is like a bucket in memory, and we're updating values in it. And every time you use it, it's gonna use the most recent values. So whatever is on the right-hand side is using the most recent values of X. Now I have a problem over here with you defining this as MP.0s, okay? Can someone help me explain why this is, it's okay, but why it's not general enough?
Shouldn't you use the X0 vector for your initial guess?
Yes, so the X guess. So Natalie is telling us that instead of using, if you use MP.0s, what you're effectively doing is you're always defining your guess as 0. You're not using whatever guess the user has provided. So instead of this, what I would do is just do mp.array and model it on X guess. Okay. So all I'm saying is I'm starting my solution vector with X guess. Okay. So now we can compare.
Hey, Professor.
Yes.
My code is giving me an error in the error line, the norm of b minus a dots parentheses x comma 2. I do not know why it's giving me an error.
So did you import the norm? So what is the error saying?
I imported. It just says invalid syntax.
Braden, I figured that out earlier. It was it's in the Jacobi function. In that error line, it says old. It should say x old.
X old.
Oh, thank you.
Yeah. Okay. All right. So it looks like you guys got it. Okay. So let's now go ahead and compare. I actually have an error over here too.
Probably the same one.
Old.
You just have to
we have old.
write X.
Oh, should be X old. Good catch. All right. So yeah, you see, when you see the error, name old is not defined, right? So you just search for old. Just what I did. I put Command F old, and I found where that was, and then fix that. Okay. So now what I'm doing, I'm setting a tolerance 10 to the minus 4, and I'm printing the Jacobi solution and the Gauss-Seidel solution. So they will stop at the same tolerance, which is 10 to the minus 4. Look at that. The Jacobi took 23 iterations to get there. The Gauss-Seidel took 9 iterations. Okay. Actually, I have something wrong over here. Sorry. BX0. Apologies. Okay. Sorry. It took 19 iterations for the Jacobi and 9 iterations for Gauss-Seidel to reach the same tolerance. Okay. You're going to see something similar in your homework 4, which is again not due to date. But we're going to apply it for the more realistic problem. Okay. All right.
Professor, I still have that same error in the Gauss-Seidel with the error. That
What
error
is the error
equals
telling you?
norm. It still says invalid syntax for error equals norm of b minus a dot of x comma 2 in the Gauss-Seidel section.
Okay, and have you imported the norm function?
I imported all of those, yes. I
Okay,
restarted
so
my kernel and ran all as well.
Try, instead of using the @ symbol, try dot, like I'm showing here, dot x. On some systems, the @ symbol is not defined. So try this. And you probably want to do it also for the Jacobi. It's just another way of multiplying matrix by a vector, matrix row and vector.
It's still giving me that same
okay,
error.
We can talk after class. Okay, we can talk after class. There's probably something off with your system. Yeah.
I just have a question. So when we look at the Jacobi solution and we look at the error term, it starts out around 8 and then keeps, 8, 3, 2, 1, 0 and keeps getting smaller.
Mm-hmm.
But when we go to the Gauss-Seidel, it starts at 8, 2, 3, 2, 0. But then the very last term jumps back up to 9. Oh, that's 9
10 to the minus 5. Okay.
Yeah, I didn't see that. Thank you.
All right. Okay. Now we're going to talk about our last iterative solver, which is one more improvement to the Gauss-Seidel method. Okay, and this digs into a little bit more theory of iterative solvers. And the idea for iterative solvers is as follows. If you think about an iterative solver as a recipe taking you from a guess xk or a current state xk to another state xk plus 1, that recipe defines a vector from xk to xk plus 1. Okay. That vector, you can literally define it as the difference between xk plus 1 and xk. Excuse me. Now, this R is effectively the recipe. This could be Jacobi, this could be Gauss-Seidel. This is the recipe that takes you from xk to xk plus 1. So R Jacobi is simply that. Remember in the Jacobi formula, we said new equal old plus something. That something is this R. Okay, so there's an R for Jacobi, and then there's an R for Gauss-Seidel. For Jacobi, you use the old information. For Gauss-Seidel, you use the most recent. But they look the same, it's just an R. Okay. Now, looking at that definition, then you can generalize iterative solvers by saying the new value of an iterative solver is equal to the old value plus this recipe, R. Okay. Now, what if we want to move faster along R? So think of R as giving you as the direction vector, okay, from xk to xk plus 1. What if we amplify that vector so that we move faster in that direction? In other words, what if we multiply our recipe by a number? Just take that recipe and scale it by a number. This is called successive over relaxation. Doing this simple change might actually even cut your iterations from Gauss-Seidel by possibly a factor of 2 or 4 or 5, just doing this simple change. We call omega the relaxation parameter. So we typically, in practice, we typically choose the recipe to be the Gauss-Seidel recipe. And if Gauss-Seidel is chosen, then that's called the successive over relaxation method. And you simply take the Gauss-Seidel method and multiply by a omega number. You can do this in your code right now and see what happens. In practice, omega needs to be between 0 and 2. Actually, not less than equal to 2. This should be strictly less than 2, otherwise it's going to diverge. Okay, should be less than 2. Okay. Turns out that for different systems, there is an optimum value of omega. Omega might actually cause you to do more iterations rather than less iterations. I used to have a homework assignment on successive over-relaxation, but I'm not going to give you that this year. But I just wanted to share with you the successive over-relaxation method. And with this, we are really done with linear solvers. And I'm going to give you a 3-minute break now. And I will see you in 3 minutes, where I'll show you the next steps in iterative methods, what we do in practice and other complexities for your own information. Okay, but as far as the material you're responsible for, we end here. Okay, so I'll give you a 3-minute break. I'll see you in 3 minutes.
Hey, Professor. I have a question about the code.
Natalie, can we chat after the class, please?
Okay.
And Braden too. All right, I'll see you in 3 minutes. Zoom recording. Hope everyone is back. Okay, the next, excuse me, the next few slides, I would like to talk to you about what we deal with in practice with iterative solvers and linear algebra systems. The most compelling thing to look at is how we store our matrices. So what we looked at in class were simple tridiagonal matrices where you just had to deal with 3 diagonals and like a few hundred points. And you had worst case when you wanted to compare the tridiagonal, the Thomas algorithm with the direct solver or the built-in solve methods, you built a full representation of the sparse matrix. That wasn't very costly, but in real life and in practice, we have pentadiagonal systems and systems that have that are septadiagonal, like the septopus, that have 7 non-zero diagonals, or even just randomly populated sparse matrices, and where we cannot just store the 3 diagonals as 3 vectors, where we got to store the non-zero entries. And so there needs to be a mechanism where we can store these complex matrices, these expensive matrices, these big matrices efficiently. Remember, each entry is in a matrix, even if it's 0, is represented as a floating point number, which could be 32-bit in length or 64 bits. And then when you take large systems of equations, those could really add up. So let me give you an example. And this is a very simple example. If you are solving this equation, this is called the Laplacian. This describes heat transfer. Anything that has a second derivative, we will learn that when we do ODEs. And I guarantee you that I will teach you ODEs better than what you will learn in math, okay? Because I'm gonna adopt a physics approach, okay? But until we get there, second derivatives typically describe what we call diffusion processes. Things like heat that is diffusing slowly, or concentration. You're standing and then you put a drop of ink in water and starts diffusing slowly. Those are all described by second derivatives. In multiple dimensions, this second derivative is given by this symbol called nabla, or the del operator. And del squared or nabla squared u, or u being could be temperature, could be pressure, could be some quantity that's diffusing. This gives you, this is a heat transfer equation, okay? Now, the discretization of this equation, the same way we did the heat transfer problem, we can turn this continuous equation into a set of algebraic equations that relate different points to each other. In 1D, you have n points. In 2D, you have n by n, right? It's a 2D plate. Think of a plate being heated. In 3D, you might have like a cube where you're doing n by n by n points, okay? Now, to represent the equations as a matrix, as a dense matrix, forget about the zeros. Let's say you're storing everything in the matrix, including the zeros, okay? All of those result in sparse matrices, by the way, because you only have 3 or 5 or 7 non-zero diagonals. That's all, okay? So they are sparse matrices, but if you want to represent them in a dense way, this is the number of entries in the matrix. So for n equations, you have n by n. For n squared equations, you have n squared by n squared matrix. And for n cubed equations, you have n cubed by n cubed matrix, okay? So in 1D, this is the total number of entries in the matrix, the total number of coefficients in the matrix. Storage requirements now for the 3D Laplacian, this last one, this last guy over here. Let me annotate this guy. Just out of curiosity, let me show you this requirements. For 16 points, that's nothing. There's just 16 points in each direction. That's horrible. Takes about 128 megabytes to store this matrix. For 32 points, only 32, that's still nothing. In each direction, it's 8 gigabytes to store this one matrix. And for 64, it's 512 gigabytes. 512 gigabytes. That's as much as I have memory on my computer at home. Okay? Actually, much more. So it's horrible. It's really, really bad to store dense matrices. Okay? The idea now is that, okay, instead of storing everything in the matrix, all the zeros, how about we store only the non-zero entries? Okay, we save the non-zero entries and figure out a way to access those entries. Remember, you still want the niceness of indexing a matrix as Aij. So you need to be able to access coefficients in the matrix randomly. So we can store the entries, the non-zero entries, and then concurrently store another array that tells us that this entry is located at this location in the matrix. And that entry is located at this ij in the matrix, and so on and so forth. When you do that, you can reduce your storage significantly. If you have k non-zeros per equation, this reduces storage, for example, from n squared to kn for a one-dimensional matrix. Okay. Now let me show you the comparison of what happens when you change from a dense matrix to a sparse matrix representation. For a 3D case, you're storing n cubed by n cubed entries. When you do it as a sparse representation, you're only storing 7 times n cubed entries. In practice, for 3D, the dense take the 64 number of points case, you went from 512 gigabytes of memory to 14 megabytes. Okay. For 16 points, you went from 128 megabytes to 0.22. So that's important. Okay. I'm showing you here how you can create a sparse matrix in Python. And the great thing is that you can access entries in the matrix as if you are accessing a full dense matrix, except you're storing it in a very cheap way. I'm not gonna spend time on this. I'll let you, if you want to dwell on it, ask me later. Go for it. That's for your future. Okay, remember that we talked about this in Dr. Saad's class. So later on, you have a big sparse matrix. You're like, how do I do this? Go back to these slides and email me. Okay. The best thing you can do after you've met me is 2 years down the road, send me an email. Hey, Professor Saad, I'm doing this problem and I thought I could use some of the things we learned in class. Can you help me with this? Do you think this is a good idea? That is my greatest honor and the greatest thing you can do for me. And of course, if you're walking around campus and you see me, now you don't know how I look with a mask. Maybe I should show you how I look with a mask on, but this is how I look with a mask, okay? Anyway, my newborn boy thinks that people look like this. They have like eyes and a little nose bridge and just something over here. When he sees people without a mask, he's like, huh? Okay, iterative solvers in Python. Python has a huge array of complex iterative solvers. It's Jacobi, SOR, Jacobi, Gauss-Seidel, and successive over-relaxation are just like, you're just barely touching the surface of the world of iterative solvers. In Python, there are hundreds of other solvers that you can access with the SciPy library. So you can go to this link, they explain to you a bunch of what solvers there are. There's the SP-solve, which is a efficient direct solver for sparse systems. There's the conjugate gradient method, generalized minimum residual. I'm just showing off here. There's the biconjugate gradient method, biconjugate gradient stabilized, the LG, MRes, MinRes, et cetera, hundreds of solvers. The fastest solver in my world is what's called the algebraic multigrid solver. And who was it last Tuesday who told me they wanted to plot how the iterations converge, and you see kind of this oscillatory behavior. And the algebraic multigrid, so whoever said that, I'm sorry, I forgot your name, but whoever said that, I told you there's something in the algebraic multigrid that leverages that. We noticed that iterative solvers are really good when there is large error initially, and then they slow down. So what the algebraic multigrid solver does, it tricks the system to always keep the error, to perceive that the error is large. There's a very smart way of doing that. And it's one of the fastest converging solvers on Earth, okay? It's called the algebraic multigrid solver. In Python, there's an implementation of that called PyAMG. You do not have access to that on Jupyter Hub with CHPC, but locally you can install it with Anaconda, okay? And some other solvers, like I said, a bunch of other solvers in Python. And I give you an example of how to use a sparse matrix with one of the biconjugate solvers. And the last slide I want to show you is actually one of the first slides I showed you in the semester, comparing direct versus iterative solvers. So what I'm doing here, I'm taking the Laplacian. So this is taking the Laplacian and putting something on the right-hand side. So that makes it what's called the Poisson equation. It's another heat transfer equation with a source term. And I'm solving this in 2D, okay, with a random source term, random heating, okay, in the domain. And I'm solving this with a direct solver. So that's like what you learned, Gaussian elimination, and conjugate gradient, sparse solver, and the Braic multigrid, versus the number of points in each direction. And this is what you get. So I'm plotting the solver time, how much it takes to solve this system of equations, versus the number of equations or the number of grid points, okay? Sorry, the number of grid points in each direction. So really the size of the matrix is n by n. So you start early on for like 10, 15 points. They're all the same. Blue is the direct method. Conjugate gradient is these yellow disks. SP-solve, that's another solver in Python, is these black squares, and the AMG are these red pentagons, okay? Look for yourself. Almost in every case, the cost of the solver eventually starts going up exponentially. Direct method goes up early on, like by 50 by 50. There's no way, it just spikes up. Then you go to the conjugate gradient method. It's fairly stable as you increase the number of grid points, but then it also exponentially goes up. But look at the algebraic multigrid, so beautiful. It just almost stays the same cost as you increase the number of points, okay? In my research, we use a conjugate gradient method with a full multigrid. There's another version, there's another type of multigrid called the full multigrid. As a preconditioner, it gets really complicated to get the best and fastest convergence, okay? Whole world out there, all right? And you will learn about that if you end up doing graduate studies here and work with me, okay, which I highly recommend, okay? But that's a few years down the road for you, okay? And with that, I conclude the series on linear solvers. And we can chat now if you want, and we can chat about your code. But actually, since I have you here, let me ask you this. Would you be okay if we do live streaming on YouTube? So I'll broadcast on YouTube, and you'll be here on Zoom, sitting, waiting on Zoom if you want to ask a question, but we're doing live on YouTube. There's a 10-second delay, 7, 10, 15 seconds maybe, okay? So I want to interact with you live in person, because on YouTube you can only chat, asking questions. Okay, so would you be okay if we try that out next time? We do the live stream, you're watching it on your computers, okay, on YouTube. And then once you get to a, so in real life, I'm ahead of what YouTube is doing, okay? So maybe every now and then I take a pause for 10 seconds for all of us to kind of just synchronize, and then you can ask, we can discuss. Do you want to try that out? Would you be interested in doing that? Let's do a poll, actually. Let me see if I can create a poll. I have to pre-create the poll. Okay. YouTube live stream. You listen to trying out a YouTube live stream and ask questions on Zoom. There will be a delay between stream and questions. Okay. Yes. No way. Okay. So 2 questions. Let me see if I can do this poll. YouTube live stream. Okay. I just launched a poll. I'm gonna vote yes. Oh, I cannot vote. Oh, there's 1 person, 2 who said no way, 3 who said no way, 4 who said no way, 5, 6.
I have a question. Why is it that what is like, I guess, the more beneficial point of doing it on YouTube? I guess what is like, what are we gaining from that?
I will be in the slides. I will be standing with the slides next to me. I'll be moving around rather than you just seeing this dull screen with slides in it and me talking in the background. Sorry, I hope, I imagine that was not clear. So to clarify to everyone, the problem with doing it in Zoom is that Zoom cannot keep up with me moving around and buffering and sending the message, the video to you. It's going to destroy quality. Okay, on YouTube, you're going to get, if you want to stick around, I can show you an example right now. It will take me 2 minutes to do a live stream on YouTube, and while you stay on Zoom and you watch the YouTube, okay? And you'll see the difference. You're going to get HD quality with me in the slides. Look, it's more effort for me because I need to create this huge setup over here with the lights and the screens and my camera. But I think it gives a better experience, okay? Okay. To me, the delay just doesn't seem worth it. Okay. Hey, if you can donate a few minutes of your time, let's try it now. What do you say? Okay. Especially those who disagree. Okay, so we're gonna have to figure out a way to deal with the delay, right? So you can send a message on chat. I will be able to see the chat on YouTube, but we can also set, after every few slides, I can pause to synchronize, okay? In my opinion, this will be you will retain more because I am in the slides, okay? If you can spare a few minutes right now, I can try a live stream, okay? And I'll give you the link in the Zoom chat. Just give me a moment, please. I'm gonna switch this back. Right. Okay. Slideshow in window. Okay. So keep tuned on the chat, please. And I'm gonna have to open up YouTube. Gonna end up being like one of those what they call them, influencers on YouTube and Instagram. Okay, gallery. Let's see everyone over here. Okay, give me a second. Start streaming. Okay, and I'm gonna share with you the link to the video in the chat. Now go open up your browser and let's just go ahead and try it out. You know, I'm gonna keep my video here, but I'm gonna look like a crazy person standing on the wall and waving around. But on YouTube, you're gonna see me on top of my slides, okay? Are you on YouTube? Okay. So I'm gonna mute my audio on Zoom.
Yeah.
Yes.
The delay is really not that bad, to be honest.
And the quality is way better.
This is the first time I felt like I've been in a classroom since
Isn't it?
March.
So now I'm back on Zoom.
When you unmute yourself on Zoom, there's like an echo from the YouTube.
Echo, for sure. Yeah. Oh, I can see if I can pause this.
Or maybe you could just answer on YouTube and just
I can
hear
do
us.
that. Sure. Yes, actually, then go ahead and talk in the Zoom. This is actually a good idea, Sam. Listen on YouTube and ask me on Zoom. I'll probably be a slide away, but I think it's okay. Right? We can deal with it. But look at this in experience. I hope you're still on YouTube.
YouTube is paused, I think.
Yes, I paused it for a second. Yeah.
So would we just interrupt you if we have a question in the middle?
You can hear us now, right? Can you see the YouTube chat while you're presenting?
So I stopped the stream and I'm back on Zoom to chat with you. I'm just trying a few ideas out, okay? So let's say I'm chatting with you now. What do you think the matrix storage is gonna be for 3D case?
512 GB.
Sure, yes, exactly. And then we can say, okay, now I'm gonna switch back to YouTube, okay? And then I start streaming. And now you're on Zoom and you can take the question from YouTube and answer on Zoom. You know, we're gonna have to figure it out because there's no live stream platform that allows the audience to go on record because there's this delay. There's always delay. So let me then ask again for those who said, maybe I can redo the poll, okay? I'm gonna relaunch the poll and see if you've changed your mind now that you've seen the quality of the product that we can do if we do a live stream.
I have another question.
Yes, Cole.
So I guess one thing is are they going to be recorded still, and will we have access to the lectures? Okay.
Of course. I mean, that's, and it will be a better recording where I'm just lecturing. It will be pure uninterrupted lecture, I would imagine, because then you don't have the constant interruptions, right? I would probably pause the stream, or get your answer on Zoom and then repeat the question or the answer. Okay, but it will be just me without kind of interruptions from other windows with Zoom, etc. I'm gonna relaunch this and see if you've changed your mind. Okay, we still got two no way. Would you mind just telling me what your concern is?
Professor, I voted a yes, but the thing is, I have a question. So how will the recording be posted on the YouTube? Like, do you have like a Zoom question video and the one that you're doing live streaming together? Or like, how does it work?
I will be recording just the live stream the chat on the live stream will be replayed in real time. When I get questions on Zoom, I will repeat those questions in person on the live stream. So I would say, so Veet asked me, about the total cost when we go to, 500 points, for example, and et cetera, et cetera. Okay, but we can still hold the discussion.
Yeah,
We will still hold the
that works.
discussion. We can still hold the discussion on Zoom. We will pause the live stream, hold the discussion on Zoom. Okay.
Yeah, sounds good. Then it's good. It's a good idea.
But we don't. I don't think we need to record the discussion in and of itself. Okay, and I can record the salient points. So what are other concerns? And honestly, if you have ideas or thoughts, since you're more tech savvy probably than I am, or you've seen what people do on Facebook Live and Instagram, send me ideas of how we can do this better.
The only question is, so when we do the code, so we're doing the code in the discussion, right? So when you're asking
no. We will do the code. Okay, go back on YouTube, Sovit.
Okay, yeah.
Okay, did you see that, Sovit?
Yeah, now it's saying an error occurred. Please try again later. So let me
because
try
I
to
paused
do that again.
because I paused the stream.
Oh yeah. And now it's there. Yeah.
I wish we had. I don't know. I mean, to me, it is easier to do the slides on Zoom. Okay.
Yeah, we can do that. We can do that,
I
Professor.
think,
I mean, sounds good.
Okay. All right. Any other tips or comments for this live stream video thing? Look, we can try it. Yes. Natalie?
My main concern is like when we ask a question with our audio, would we have to wait until you paused for questions to ask?
So no, because you will be actually behind, right? So I'm ahead of you, 10 seconds ahead of you. And as you're watching, you see something and you ask a question, then I'll pause and answer you. But from your perspective, it's happening in real time. Okay. From my perspective, there's a delay. So we can ask in real time, or we can say, okay, this asking in real time is not working. Let's maybe try doing pause from now on. I mean, I don't know the answers to all of this. No one that I know of has ever tried doing live streaming and Zoom at the same time. So typically what other professors do, if they're doing the live stream, you're limited only to chat, okay, on the live stream.
It seems like we'd have to choose which chat to use, and it seems like it'd make more sense to use the YouTube chat and then just use use Zoom for audio when we want to ask something.
I agree. Good feedback. I say we try it. Hey, let's just try it. It might be a total disaster, or it might be like, look, it was a better learning experience. I know in one of the early lectures, everyone was like, yeah, this is much better when you are in the slides. So it might be worth your time saying, look, this is better, even if there's going to be a delay in the questions, we can reserve the questions and keep them till the end. We switch on Zoom and then I share my slides with you. So on my end, if you see my screens here, I have like 15 windows. It's a total nightmare. Okay. So, but I think it's a better experience anyway, and it keeps me honestly more engaged. I don't like sitting and talk. I like to be standing and moving around. All right. Okay. So some of you had questions about coding, and I apologize for keeping you waiting. I'm gonna let you share your screens with me. We had Braden and then Natalie, correct?
Yes.
Okay, who wants to start? You want to start, Braden?
Sure. I didn't realize. All right. So right here, it's giving me an error for my error code. And so coming up to the top, I've ran this cell, running all of them, coming down, and it just keeps saying invalid syntax. And I'm trying to figure out why it is, because we've got the parentheses are closed for both parentheses. We have the comma separating. I just don't know what's going on. And I don't know if it's a line above, because whenever I try and comment out the line, it still gives
That's
me
not the
this
line. This is line 16. So comment line 16. This is line 16. The error, okay, read the error. Line 16. You see it? So it's line 16 is this second one. So comment this one out. Okay, so I think you have an issue with tabs, with the tabs, I think. So do this, redo all the tabs. So delete them all, give them, and then tab them up, not space. So I think you might have an issue with indentation. Okay. Interesting. Count +1. Okay, this looks fine. This looks fine. Okay, this looks fine. The for loop. Okay, same for X. Can you let me, I wonder if I can control your, okay, yeah. Okay, enter.
Should this return be, should the
No,
return be here?
No, outside the while loop, no. Okay. Yep. So enter.
I think that there's remote control, give you access. There you go.
Okay. Okay. So when you press Shift Enter, gives you this valid syntax. While count less than 10. Trying to figure out. Oh, you're missing a parenthesis. There you go.
Oh, that's why.
Yep. All right. Natalie, do you want to share?
Yes. Just 1 second.
It's always the stupidly easy things, isn't it?
That's right. Sometimes these parentheses could drive you crazy. All right.
Okay, so basically, I just have a question about how the code is working. So first, when you do a method and then you have your parameters, when you first write A, comma B, comma XGuess, comma tolerance, is that initializing those variables?
No.
So,
all you're saying to the function is I expect a variable here and a variable there and a variable there. Okay. And you always assume that once you are inside the function that you have access to those variables. Okay. but it doesn't initialize them.
So then for the Jacobi one, I'm just wondering because you have X guess as a parameter, but I'm not seeing where you set X guess to something.
Well, X guess is an input. Why? So if it's an argument in the function, it's usually an input. Okay.
So
the
if you
user
scroll down
provides
to the bottom,
X guess. Yeah.
Scroll down to the
So this
bottom.
X0, this X0, when we call Jacobi, A X0, but actually you should change the order of the parameters. It should be A B X0 because we changed the function call, I think, last time.
So like the order does matter, right?
Of course, absolutely. Because inside
So
that function, whatever you're bringing in on the third entry, you're calling that X guess, and you use that.
and I'm just wondering, like, the number of parameters is what you have to have in the same order when you call the function, right? Okay, so basically you're setting X guess to the X0 matrix when you call it.
The X0 array.
Yeah, the X0 array.
Yeah, so we call Jacobi. On the third argument, we give it X0. When Jacobi is called, X0, X guess is a representation of X0. So forget X0 and X guess. They're called differently, but in the context of Jacobi, it's called X guess. Okay. That's why we make it a function. So you can use different names, different variable names. Doesn't have to be the same name. So
So let's say I wanted to try a different X guess without like recopying the function. I just want to call it again. I could have another function called x1, and then I could
a function, a variable, another variable.
Or yeah, another.
Or
yeah,
call it my X guess, whatever you want to call it, and then call Jacobi again.
And then call Jacobi again, and then instead of X0, I can put X1, which I could put X1 right here with 4 different
whatever you
numbers.
want, whatever you want to put it. Yep, doesn't matter.
Okay. Yeah, that helps. Okay.
All right. I'll see you all next Tuesday.
Okay, thank you.
Bye-bye.
Hey, Professor, quick question. I know that there's office hours today with Dylan. Is there any chance that I can have you just quickly explain what we're supposed to be doing for part 2 of the homework?
For what?
For part 2 of the homework that's due tonight. I was just confused on what it's even asking us to do.
Okay, let me pause the recording.